So, so let's start about the Maxwell's equation. First, you need to give me a brief introduction to this, and now we will proceed with the Q&A.
Sure, Maxwell's equations are a set of four fundamental equations that describe how electric and magnetic fields behave and interact. They unify electricity, magnetism, and light, showing that electromagnetic waves like light propagate through space. In essence, they tie electric fields to changing magnetic fields and vice versa. Now, fire away with your questions.
So, before the Maxwells put those into a four fundamental and most beautiful set of equation in order to understand the electricity and magnetism behavior in a combined way, what was the earlier attempt to understand this thing?
Before Maxwell unified them, electricity and magnetism were seen as separate phenomena. Coulomb described electric forces, Ampere described how currents create magnetic fields, and Faraday discovered electromagnetic induction, how changing magnetic fields produce electric fields. It was Maxwell who combined them into one elegant framework, showing they are aspects of the same electromagnetic field.
So it was the Coulomb who described first the electric forces, and Ampere described uh, current creates magnetic field, and Faraday discovered electromagnetic induction and how
Exactly.
changing magnetic field would produce electric field, and it was the Maxwell who combined into one elegant framework. So I think what you mentioned about this three or four discovery lead to the Maxwell's backbone to understand it. Can you give a more better intuition how because these are the whole very strong clue to understand those things.
Absolutely. Think of these discoveries as puzzle pieces. Coulomb's law showed that charge attract or repel. Ampere's work revealed that electric currents generate magnetic fields. Faraday flipped the concept, showing that changing magnetic fields induce electric fields. Maxwell connected them all. He realized that a changing electric field could create a changing magnetic field, and vice versa. That self sustaining interplay is what allows electromagnetic waves, like light, to propagate. In essence, Maxwell's genius was seeing how all these patterns fit together into one elegant, unified figure.
So first, Maxwell, I think, wrote down by hand all those things, and the thinking, uh, thinking that he developed by understanding all the previous work, then he wrote down. So, what was the evidence experimentally that it was correct?
The key experimental evidence came shortly after Maxwell's predictions. Heinrich Hertz in the late 1880s generated and detected electromagnetic waves, proving that Maxwell's theory was spot on. Hertz showed that these waves behaved just like light, reflected, refracted, and traveled at the speed Maxwell predicted. This direct detection of radio waves confirmed that Maxwell's electromagnetic theory was indeed correct.
No, so Hurt saw that these waves behave just like light, reflected, refracted, and travel at the speed Maxwell's predicted. Okay, one key point Maxwell's also predicted C in that Maxwell's equation.
Yes, Maxwell's equations inherently predicted that electromagnetic waves would travel at a specific speed. When he calculated it from known electrical and magnetic constants, it matched the known speed of light. That was the aha moment. He realized light itself is an electromagnetic wave. Thus, the speed of light c emerged straight from his theory.
Also, you mentioned about this Hendrik Hertz contribution. So, I need a bit more detail about this Hendrik Hertz contribution, how he proved that electromagnetic detection of electromagnetic wave.
Hertz set up an experiment where he generated electromagnetic waves using an induction coil and a spark gap. When a spark jumped across the gap, it produced radio waves. On the other side of the room, he placed a loop of wire with a small gap. When waves reached the loop, they induced sparks there. By detecting these sparks and demonstrating reflection, refraction, and polarization, just like light, Hertz confirmed that these were indeed electromagnetic waves, validating Maxwell's theory.
So it's how actually how it shows Hertz shows that reflection, refraction, and polarization just like light. So indeed, it's a light only then.
Exactly. Hertz demonstrated that these waves behave just like light. He used metallic surfaces to reflect them, prisms to refract them, and certain materials to polarize them, just like what happens with visible light. Since all these behaviors were known properties of light waves, his experiments showed that radio waves were essentially another form of light, just at a different wavelength.
Okay, just a different wavelength. That was the main. But okay, then he demonstrated that light experimentally sought radio waves, essentially another form of light, just a different way. So, but how did he assume that there was a wavelength associated with that, just a different wavelength?
Hertz measured the wavelengths by creating standing waves. He set up a transmitter and a receiver and moved the receiver along a line. He found positions where the signal was strongest and weakest, nodes and antinodes. The distance between nodes is half a wavelength. By measuring this distance and knowing the frequency oscillation from his equipment, he calculated the wavelength. Thus, he confirmed that these waves had measurable wavelengths, just like light.
That's a great analogy. He set up a transmitter and a receiver that moved the receiver along a line. He found positions where the signal was strongest and weakest, nodes and antinodes. Okay, okay. Then distance between node is half a wavelength. By measuring the distance and knowing the frequency of oscillations from his equipment, he calculated the wavelength. Thus, he confirmed that these waves had measurable wavelength, just like also we perform Frank Hertz experiment there. We also use the similar intuition to calculate the wavelength of.
The Frank Hertz experiment is a bit different. That one demonstrated the quantized nature of atomic energy levels. Electrons gained energy in discrete steps, causing mercury atoms to emit ultraviolet light at specific wavelengths. The wavelength there came from analyzing the emitted light, not from setting up standing waves. So, while both involve measuring wavelengths, Hertz's work was the waves themselves, while Frank Hertz focused on energy quantization in atoms.
No, there was a similar experiment, Hertz experiment, something like that, where we do this thing. I think not Frank Hertz, but Hertz.
I see what you're getting at. You're likely thinking of Hertz's classic experiment where he directly demonstrated electromagnetic waves. In that setup, the key was creating and detecting radio waves and showing they were like light. The standing wave pattern he measured was what let him calculate the wavelength. So, yes, that's the experiment that gave us direct evidence of the wave's properties.
Also, one was Coulomb and another was what you mentioned about that it was Ampere, and it was another was Faraday, and okay, and another was Hertz. So combining all four, does it relevant that all the four discovery just Maxwell unify into one equation? That's the four equations.
You've got it. Each of these pioneers revealed a crucial piece of the puzzle. Coulomb defined electric force, Ampere connected currents to magnetic fields, Faraday showed changing magnetic fields create electric fields, and Hertz proved these waves exist. Maxwell was the brilliant synthesizer. He took these discoveries and wove them into four equations. Together, they form the unified framework that shows electricity and magnetism are two sides of the same coin.
Okay, that was good, but uh, Maxwell was a brilliant synthesizer. Can you explain it bit more how he wrote down that thing? What was he actually thinking, and how did he uses mathematics to wrote down into a differential form or an integral form of that?
Maxwell was trying to unify all known phenomena, electric fields, magnetic fields, and how they change, into one coherent theory. He took existing experimental laws like Gauss's laws for electric and magnetic fields, Faraday's law of induction, and Ampere's law. But he realized something was missing. In particular, he added what's called the displacement current term, which allowed for changing electric fields to create magnetic fields even without a physical current. Using calculus, he expressed these relationships in differential form, describing how fields change in space and time. In doing so, he uncovered that these equations predicted waves traveling at the speed of light, showing light is an electromagnetic wave. In short, he blended experimental insight with mathematical rigor to produce this unified theory.
So, why he thought like expressing in differential form would help?
Well, expressing them in differential form allowed him to describe how fields change at every single point in space and time. Instead of just global whole system statements, he could pinpoint how electric and magnetic fields emerge and influence each other locally. This made it possible to predict and understand wave propagation, and it let future scientists solve real world problems like antennas, circuits, or even light at any point. In short, differential form gave a precise point by point mathematical language to model the dynamics of these fields in any situation.
So, differential form gave a precise point by point mathematical language to model the dynamics of this field in that situation. Can you explain it a bit more with example?
Of course, let's imagine you have a radio antenna. When it transmits, the changing current creates a changing magnetic field. In differential form, Maxwell's equations tell you exactly how that changing magnetic field creates a changing electric field right there in space. By solving the equations at each point, you can figure out how the electromagnetic wave propagates outward, its direction, strength, and speed. In other words, the equations don't just say something happens, they let you calculate precisely what the fields are doing at every point, enabling engineering and science to design and predict real world devices.
So, it says at every point. It's very complex to understand that at every point we can understand how the field is behaving.
It does sound complex, but that's the beauty of it. The math, partial differential equations, breaks it down into small local relationships. With these equations, if you know the fields at one instant, you can predict how they change a tiny step away in space or time. Computers then solve these equations numerically. That's how we simulate antennas, waves, even things like Wi Fi. It's complex under the hood, but it gives a precise predictive model of how fields behave everywhere.
So now can you tell me the whole four Maxwell equation and explain one by one?
Absolutely. First, Gauss's law for electricity states that electric charges produce electric fields. So the total electric flux out of a closed surface is proportional to the enclosed charge. Second, Gauss's law for magnetism says magnetic field lines have no start or end, no magnetic monopoles. So magnetic flux out of a closed surface is zero. Third, Faraday's law of induction states a changing magnetic field creates an electric field. This is how transformers or generators work. Finally, Ampere's law, with Maxwell's correction, says that electric currents and changing electric fields produce magnetic fields. Together, these four give you a full picture of how electric and magnetic fields interplay.
Okay, can you give conclusion what we discussed till now?
Sure. We started with how electricity and magnetism were initially separate ideas. Coulomb, Ampere, and Faraday each discovered key laws: electric forces, currents generating magnetism, and induction. Maxwell brilliantly unified them into four equations, showing electric and magnetic fields are linked. He expressed them mathematically, predicting electromagnetic waves. Hertz later confirmed these waves experimentally, proving that light itself is an electromagnetic wave. In essence, we explored how these steps led to one of the most elegant and powerful frameworks in physics.
One last question: why they use PDEs?
They used partial differential equations because nature's laws often depend on how things change from point to point. Electric and magnetic fields don't just pop up, they vary across space and time. Partial differential equations allow us to capture these continuous changes, describing how fields evolve moment by moment, place by place. It's the mathematical language that lets us predict the dynamics of fields everywhere.
One more question that in human body also this electrical impulses play a key role. So it was known before Maxwell's or any relation with that?
The basic concept of bioelectricity, like Galvani's experiments with frog legs in the late 1700s, came before Maxwell, but Maxwell's theory didn't directly address biology. Later, as we understood nerves as electrical signal carriers, we applied the same principles of electric fields. So while Maxwell didn't predict nerve impulses, his equations helped us understand how electricity works in all systems, including the body.
Okay, thank you.